Air-insulated substations use air as an insulating medium, and therefore need to be designed carefully so the electrical energy that passes through them is controlled and kept safe. To do this, we space the equipment out using electrical clearances. By the end of this section, you'll understand what the main electrical clearance parameters are and how they are used to design the substation. The aims of the course today are: introduce the principle of electrical arcing distances and see how these are used to define the electrical clearances. Introduce the different electrical clearances that we use to design air-insulated substations. See how the different electrical clearances are applied to a typical switchgear bay. Air-insulated substations use air as an insulating medium and incorporate uninsulated, i.e. bare, metallic conductors to connect the equipments together. Because the conductors have no insulation, the electricity will jump from the conductor to any object that approaches them. Here's a typical bare conductor. Once the object gets to within a certain distance of the live conductor, it will break down the air, an arc will be formed, and the object will become live. Here are some typical arcing distances. As you can see, as the system voltage increases, the electrical arcing distance in air also increases. At 69,000 volts or 69 kV, the electrical arcing distance in air is 172 millimeters. When we go up to 400,000 volts or 400 kV, the electrical arcing distance is over a meter. The higher the voltage applied to the conductor, the farther the electricity will jump through the air. The distance that the electricity can jump is called the arcing distance. The arcing distances depend on the weather. When it's raining or humid, the electricity can use the moisture to break down the air more easily. The electrical system operators know the worst-case arcing distances and use this information to set safe minimum distances from live equipments, which increase as the system voltage increases. These are called safety clearances. For clearances inside air-insulated substations, the main aim is to keep personnel and equipment safe. To do this, we need to make some assumptions on the typical reach of the human body. For a person standing on the ground, we assume that the maximum height they can reach is 2.4 meters. When they stretch their arms out, we assume that the maximum distance from hand to hand is 2.1 meters. We then add the arcing distances from the previous table to these distances, and then add a suitable safety margin. Let's now look at a typical utilities table of electrical clearances. As you would expect, as the system voltage increases, all of the electrical clearance distances also increase. In the first two columns, we have the minimum face-to-ground clearance and the minimum face-to-phase clearance. These are purely design clearances and are used to define the minimum distances between the electrical equipment. The next column is the minimum insulation height, which is the distance to the bottom of the insulator. This is based on the 2.4 meter reach of a typical person. In the final column, we have the safe working clearance, sometimes called the sectional clearance. This is used to define safe working distances to the work areas that we need inside the substation to do maintenance on equipment. Let's now see how all these safety clearances are used to design an air-insulated substation. In my career, the main clearance infringements in air-insulated substations has come from personnel accidentally infringing the clearances by carrying equipment inside the substation, such as metal ladders or scaffolding poles. For this reason, most electrical utilities ban metal ladders inside substations and insist that wooden ladders must be used. They also have special restrictions when scaffolding is used. Firstly, let's look at the face-to-ground clearance. In most substations, all equipment structures and enclosures are bonded to ground for safety reasons. Face-to-ground clearance is a design clearance to ensure that any conductor or piece of equipment that is live cannot come into contact with any grounded equipment. Here we have an energized bare conductor in a substation. All we need to do is draw a circle around the live conductor. The radius of the circle is the minimum face-to-ground clearance distance, and no grounded equipment can be allowed to enter the circle. At 11 kV, the radius of the circle will be 500 mm. As the voltage increases, the radius of the circle increases. At 275 kV, the radius will be 2.1 meters. Let's now look at a typical transformer. Imagine that the transformer has a 400 to 33 kV ratio. The live part of the transformer is the stem at the top of each bushing. Let's now draw a circle around these elements to show the face-to-ground clearance distance. As long as the grounded transformer enclosure and all its fittings are outside these circles, we have met the minimum face-to-ground clearance. Next we have the face-to-phase clearance. Face-to-phase clearance is also a design clearance to ensure that the gap between two live conductors is high enough to prevent the electricity jumping across and bridging the gap. It is normally higher than the face-to-ground clearance, as face-to-phase, i.e. line voltages, are higher than face-to-ground voltages. The exception to this is for distribution voltages, where we cannot override the minimum requirement of 500 mm for face-to-ground clearances. Here we have a typical bus bar supported by post insulators. Assuming this is a three-phase bus bar, the distances between the bus bars will depend on the face-to-phase clearance. For 11 kV, the distance will be 250 mm. As we increase the system voltage, the distance between the bus bar also increases. At 275 kV, the distance will be at least 2.4 meters. You will see this distance applied throughout the air-insulated substation, and all the bus bars and equipment will have the same minimum distance between the live conductors. The next clearance to consider is the minimum insulation height. This is a safety clearance that was introduced to prevent personnel touching electrical insulators. Although the non-live end of insulators are attached to the grounded structure, there is still a danger of voltages tracking down the outside of the insulator due to pollution or icing. This may make them hazardous in certain conditions. And the last thing we want people to be able to do is to touch the insulator and put themselves in harm's way. To do this, we make sure that all insulators are raised a certain distance from ground level. As this is a safety clearance, the minimum distance of 2.4 meters applies across the full voltage range. The clearance distance is taken from the ground, or anything that personnel can stand on, to reach the bottom of the insulator. This includes the insulator foundation. But you will find that for the higher voltage levels, the sectional clearance takes precedence, and the bus bars are raised even farther off the ground. Most utilities will define the minimum distance to the bottom of an insulator, in addition to the normal ground and phase clearances. Although the voltage at the bottom of the insulator should in theory be zero, there is still a danger that tracking has occurred down the outside of the insulator due to pollution or rain, and you don't want people touching the bottom of the insulator if this is the case. Finally, we have the sectional clearance. This safety clearance has been introduced so that any work platforms personnel may be standing on, or safe work zones that they may need to be working in, are kept away from live conductors. The main objective is to allow maintenance or installation works to take place on one piece of equipment without having to take adjacent circuits and equipment out of service at the same time, which would obviously reduce the operational flexibility of the network. Here we have a bus bar supported by some post insulators. Most substations have a security fence around the perimeter. It's obviously important that members of the public stood outside the perimeter fence are safe. We therefore need to make sure that the perimeter fence is a defined distance away from live conductors. For 11 kV, the safe working clearance, or sectional clearance, means that the perimeter fence must be at least 2.9 meters away from the nearest live conductor. For 400 kV, the fence needs to be at least 5.5 meters away. By doing this, we've created what's called a safety zone on the other side of the fence. In this area, people can operate safely in the knowledge that they are in no danger from the live electrical equipment. The same stipulation applies where we have a roadway through the substation. The distance from the live conductor to the edge of the roadway must be at least the safe working clearance value. You will find, as you work around the world, that face-to-ground and face-to-face clearances are pretty similar whichever utility you choose to work with. However, the definition of sectional clearances and how they are applied varies widely from country to country. Some utilities use the simple approach we've used here, where we have a sectional clearance for all conditions. Other utilities have defined different horizontal and vertical sectional clearances, as well as separate minimum distances for fence lines, roadways, and bus bar heights, so it's critical that you read the utilities standard before commencing any substation layout design. Here we have a typical substation with a transformer, an isolator, and a set of bus bars. When we're designing the layout of a bay, we need to think about how we're going to maintain the equipment. Let's imagine we need to work on the transformer. Firstly, we define a safe work zone for the transformer. We then identify the nearest live conductor to the work zone. As the isolator is open, this is on the right-hand side of the isolator, which is the conductor permanently connected to the live bus bar. This is defined as the isolation point. The minimum distance from this point to the work zone should be greater than the safe working clearance. So for 66 kV, the minimum distance should be 3.1 meters. The sectional clearance also defines the height of the bus bar from the ground. The higher the voltage, the higher the bus bar needs to be. This clearance distance includes for any objects or foundations the personnel can stand on inside the substation. The face-to-earth and face-to-face clearances are fixed distances and define the equipment dimensions and spacing between the bus bars, and we can't do much to change them in an air-insulated substation. The sectional clearances depend on the operation of the substation, which gives us some options. If we followed the sectional clearances to the letter and laid out the substation in a flat configuration, it may end up being too large for the land available. A clever designer can squeeze the circuits closer together and reduce the overall substation footprint by using various techniques, including layering, to have equipment at different heights. We will look at some of these techniques in part 2 of this course, when we start to look at laying out the substation. Let's summarize what we learned today. We use at least 4 main types of electrical clearances to design air-insulated substations. These are face-to-ground, face-to-phase, minimum insulator height, and sectional. Face-to-ground or face-to-phase clearances are design clearances, whilst minimum insulator height, as sectional, as safety clearances. The clearances are used to design the substation and define the height of the equipment from the ground level and the spacing between the equipments. Congratulations for completing this course on air-insulated substations. I hope you had as much fun doing the course as I had writing it, and have learnt something important that can help you in your career. The next course will cover more advanced features of air-insulated substations. I hope to see you then.